All right, let's jump right into this explainer and decode the vast, incredibly complex world of power engineering. We're going to do this by conceptualizing the ultimate power plant blueprint. If you've ever looked at one of those massive industrial facilities, with the towering stacks, the endless mazes of pipes, and those humming generators, and wondered how a human being could possibly keep track of it all, well, you are in the exact right place. Today, we're unpacking the heavy mechanics hidden all around us by looking directly through the lens of the people trained to master them.
To build our foundational knowledge, we are drawing directly from the actual certification exam text. These questions and answers come straight from the Power Engineering 4A exam, which is this massive, grueling test of highly specific technical knowledge that aspiring engineers absolutely have to pass. But rather than just rattling off a list of facts, we've pulled the core concepts from this material so we can construct a virtual power plant together, piece by piece. To make sense of it all, we'll build this plant from the ground up. We're going to cover 1. Meet the power engineer. 2. Boilers and steam power. 3. Building the infrastructure. 4. Electrical systems and controls. And 5. Plant safety and maintenance. Okay, starting with Section 1. Meet the power engineer, the human element. Because before we talk machines, we have to talk about the professionals who run the entire show, working those demanding, rotating shifts just to keep the lights on and the factories producing.
Now, you might think the job is mostly just pulling levers or watching dials, right? But the exam reveals a completely different reality. It involves a much deeper, intense level of legal and operational responsibility that goes way beyond simple observation.
The crucial point here is that they are highly skilled, multidisciplinary workers. A power engineer holds a legal certificate of competency that literally authorizes them to act as a definitive expert. And here's a pretty wild detail. They have to document all their shift activities in logbooks, which are actual binding legal documents required by most jurisdictions in Canada. If something goes wrong, that logbook is the official legal record of the plant's history. So yeah, it's an immense responsibility.
Moving on to Section 2, Boilers and Steam Power, the heart of the plant. Let's see exactly how a fuel source gets transformed into massive, usable thermodynamic energy. Without the boiler, the plant has zero pulse.
Just think about the extreme physics at play for a second. When water converts to steam, it expands a staggering 1,600 times. I mean, imagine a single gallon of water violently expanding to fill an entire small room. That massive expansion is exactly what creates the immense pressure needed to spin giant turbines and generate electricity. The boiler's whole job is to safely contain and direct that explosive transformation.
So with water expanding so violently, controlling the exact state of that steam is absolutely critical for efficiency and for preventing equipment damage. You'd probably think turning water into regular steam is enough, but the exam materials heavily emphasize this concept of superheated steam. Why go to the extra effort and the extra expense to push that temperature even higher?
Well, the answer lies in the moisture. By pushing steam through a superheater, the temperature gets raised well above its saturation point, which dries it out completely. And that is vital, because any liquid condensation traveling at high speeds in those high-pressure lines acts like a barrage of tiny hammers. It can literally destroy turbine blades and piping. Superheating ensures the steam contains almost zero moisture, which protects the equipment and vastly improves the plant's thermal efficiency.
All right, Section 3, building the infrastructure, the skeleton. Now that we have our pumping heart generating this high-pressure, superheated steam, we need miles of piping, valves, and welds to hold it all together safely.
Choosing the right pipe is step 1. Steel is the undisputed king here. It's the absolute most common material used for general piping because of its strength. But cast iron actually has a very specific superpower. It's incredibly resistant to corrosion, making it perfect for the highly corrosive environments within the plant, like underground drainage or specific chemical lines. Of course, connecting all these pipes safely through fusion is where the real structural integrity comes in.
Because you can have the strongest steel in the world, but if your joints are weak, the whole system fails. When welders tackle thick pressure vessels, they use a multi-pass technique. But there's a major enemy here: inclusions. These are basically pieces of foreign solid matter that get accidentally trapped inside the weld. A perfect multi-pass weld has to fully penetrate and fuse with the parent metal without leaving any of those dangerous inclusions behind. That's how you get a strength weld that's just as tough as the original pipe.
Now this skeleton is packed with some highly specialized gear. Steam traps, for instance, let liquid condensate drop out while keeping the valuable steam locked inside.
Slip expansion joints allow the pipes to flex and adjust, though they do require lubrication to work properly. And if you're dealing with thick slurries or suspended solids, you definitely reach for a ball valve. Finally, you wrap the whole thing in insulation to stop heat from escaping into the room, and boom, your infrastructure's set.
Next up, Section 4, Electrical Systems and Controls, the nervous system. Let's look at how electrical currents and automated controls become the actual brains of the operation. Since a modern plant is way too complex to run on manual human input alone,
A human operator simply cannot watch every single valve, thermometer, and pressure gauge at the exact same time. If the temperature spikes in a boiler, the fuel needs to be cut instantly. So how on earth does the plant manage this massive, delicate balancing act 24 hours a day?
It relies on a super sophisticated web of control loops, which basically act as the brain's synapses. A control loop constantly asks, where are we right now and where should we be? It compares a process variable against a desired set point. If there's a mismatch, a proportional controller steps in and provides a corrective output based strictly on the size of that error. And to actually physically move a massive valve based on that tiny electrical signal, a transducer is used to convert the electrical current into a powerful pneumatic air signal. It's literally an automated ballet.
to keep track of this incredibly complex nervous system, engineers rely on process and instrumentation diagrams, or PNIDs. These blueprints map out every single sensor and valve configuration. When you look at them, you'll constantly see the letters NO and NC next to the valves. This tells the engineer whether the valve rests in a normally open or normally closed state if the power suddenly cuts out. And as you can imagine, that is a wildly critical detail for diagnosing failures safely.
Finally, we hit Section 5, Plant Safety and Maintenance, the immune system. Let's look at the safety regulations, environmental controls, and daily routines that act as the plant's active defense mechanisms to keep everything alive and completely legal.
A healthy plant lives and dies by its standard operating procedures. The exam materials break maintenance down into 4 distinct categories: routine, preventative, projects, and emergency. Juggling these 4 is basically the daily puzzle for the entire management team. You know, you might save some time and budget today by skipping a few things. The plant might even run just fine for a few weeks, maybe even months. But what is the ultimate long-term cost of ignoring that routine and preventative care? Well, it's a guaranteed recipe for total system failure tomorrow. The source material explicitly warns that neglecting basic things like oil changes and bearing lubrication will inevitably lead to a dramatic increase in unscheduled, highly stressful emergency maintenance. We're talking about the difference between scheduling a quick, cheap shutdown for a filter change versus having a multi-million-dollar turbine unexpectedly seize up on you in the middle of the night. And when true emergencies happen, like a fire, operators have to react perfectly and instantly. Knowing the difference between an electrical Class C fire and a burning metal Class D fire isn't just fun trivia, it is a vital safety requirement governed by WMIS. For instance, you'd use a foam extinguisher for Class A wood or Class B liquid fires. But burning metal, you absolutely must use a specialized dry powder extinguisher. If you use the wrong tool, you can literally cause the fire to explode. But beyond immediate physical safety, power engineers also hold the ultimate responsibility for objective environmental stewardship. They have to constantly monitor plant emissions. How do you reduce CO2? The source points out that the best way is by maximizing overall plant efficiency. Solid waste, the most environmentally sound method, is simply not generating it in the first place. They even monitor the temperature of water released back into nature. Warmer water causes thermal pollution because it can't hold as much dissolved oxygen, which actively harms aquatic ecosystems. So, having mapped out the heart, the skeleton, and the nervous system of a power plant, are you ready to take on the immense responsibility of keeping our modern world running safely? As we've seen, it takes an unbelievable amount of multidisciplinary knowledge, from thermodynamics and metallurgy to environmental science, just to grasp the basics of what a power engineer deals with every single day. Hopefully, this explainer has sparked your curiosity to look a little closer at the incredible mechanical systems hidden all around us, quietly powering our modern lives.